Hi, I'm Ben-Yaakov. This presentation is entitled Logic-Driven Spice Behavioral Sources and a demonstration on a three-phase synchronous rectifier. Now, spice has a dependent sources or behavioral sources which come in different forms in the different packages. I'm here showing it in a LT spice, but you can find it in pSpice and some other packages which are spice based. So a behavioral source, like a voltage source in the case of say LT spice, is this unit here, this device. It's a voltage source. It can be actually defined also as a current source, and it is a function of something. And this something could be an expression, could be some mathematical expression, and also it could be a function of values of voltages and currents which are real time while the simulator is running, and it will put in the right values any given time. So you pull up this window and you define here the function that you need. In general, the arbitrary behavioral voltage or current sources have many options, and I'm talking about the expression one, although there are some other options like a Laplace, which I'm not covering in this presentation. And as I've said, it could be a voltage or a current source, like this is a current source and this will be a voltage source. So if you write V equal 2, then it's a voltage source, or I equal 2, then it's a current source. Now, the nice thing about these behavioral sources, they can take not only mathematical expressions, but also logic-based, like Boolean operators, like if, and, or, and then you can combine these to have an output, in this case a voltage, which is a function of, say, voltages or currents within the circuits. So this would mean that the output voltage is according to this logical expression, which says that if VA is smaller than VB, that is A and B are voltages at nodes A and B, and the voltage at node A is smaller than at node C, then the output will be 15, else otherwise it'll be 0. Now you can combine this is then the meaning of it, and then you combine it, you can actually multiply it or take the power of it or whatever mathematical operation you'd like to do. And in this case, for example, this will be A smaller than B, A smaller than C, then it's 1 or 0, and then it's multiplied by 15. So if it's 1, then it'll be again 15 volts. So you can do many things with it, which is very, very nice. Now I'm going to demonstrate the use of such a logic expression or logic-driven source on a three-phase rectifier. A three-phase rectifier with diode would look something like that. We have here 3 phases, we have 6 diodes, and this is the load, and here are the voltages of the phases. And then what we have here is that these diodes will conduct when the voltage is in the forward direction, of course. So if I look at this situation here, for example, I have A which is high, I have B which is the lowest one, and the C is sort of in between. So therefore, this phase A, this diode will conduct, and then come back with the lowest one, which is B, while the voltage of C is in between these two, and these diodes are not conducting. So in this case, this and this diodes are conducting. Now once this rectification is taking place, then on the one hand we are going to have an output which would look like that, with some ripple on it, and the phase current will look like this. This is for half a cycle, because say if I look at the phase 3, here it's high, and then this is low and this is low, so we are going to have a current during this section here when this phase A is conducting and then phase B is conducting, and due to this change in the voltages, we're going to see this current if, of course, the load is resistive. I'm talking about a resistive load. And then we'll see a current of this shape. This is half a cycle, then in the negative half cycle with the same thing, only negative. So this is a diode three-phase bridge rectifying a three-phase source. Now we can use transistors, and the advantage of using transistors is that we can lower the voltage drop. Now in this case, of course, we have a voltage drop of a diode. If the voltages are not high, then proportionally the voltage drop of the diode is significant, and of course we're going to have a lower efficiency or higher losses due to the voltage drop of a diode, which is about 1 volt. So if the current is large, high current, then we have 1 volt times the current, and it could be quite a bit. It's 100 amp, that's 100 watts, that's a lot. Of course, the diodes are not conducting all the time, so you have to dilute it by the time to get the average power dissipation. I'm talking about the dissipation while the diode is conducting. So we can use MOSFET, and for that we'll have to turn on the MOSFET when the diode, this is the body diode of the MOSFET, and so without operating the transistor, the diode by themselves will rectify, but what we would like to do, we would like to turn on the transistor when the diode is conducting. So here are decisions to make when to turn on these transistors. I'm not talking about PWM, I'm not talking about like a buck converter or boost converter. I'm just talking about a regular rectifier that we want to lower the losses by having transistors which are in parallel to the diode, and therefore the voltage drop will depend on the RDS(on) of the transistor, and if it's a few milliohms, then we are in good shape. So this is a logic decision that we can express it as a Boolean expression, and therefore we can use this dependent voltage source. So let's have a look at a situation here in which A is high, phase A is high, phase C is the lowest one, and B is sort of in between. In this case, we would like the upper transistor of A to conduct and the lower transistor of C, this is C, to conduct. So in this case, we'll turn on A sub H, this upper transistor, if VA is larger than VB and larger than VC, and we'll turn on this one if VC is smaller than VB and also smaller than VA. Okay, so this is now this capability of this voltage source to adapt to a logic-driven type of a expression. So here is a schematics in LT-Spice that will do the job. Let me go over it in general, and then we'll go into some more details. I've put here 3 voltage sources that for the 3 phases they are shifted 120 degrees. I've put here 2 because I found that if I'll use one both for feeding the power and for sensing the potential or the voltages of the phases, then this expression somehow get a little bit tangled, and somehow it doesn't run smoothly. So therefore I've separated it. This is actually a duplicate of this, except that it is not connected to the phases. This one is only used for sensing, okay? And this one is indeed a power source to the rectifier. So we have these 3 phase sources, which are labeled A, B, C, and A1, B1, C1. Now A1, B1, C1 are connected here, A1, B1, and C1. And then I have here these behavioral sources, 6 of them, and each one has an expression. Let it know when to turn on these transistors. These are FET transistors, MOSFET transistors. So let's now zoom a little bit in. Here we see the sources these are the voltages, and this is 60 hertz, and these are the phases. Again, this is repeating itself, and here I've put 10 milliohm. Could have added a inductor, and then we see here now one of the half bridges for the C, in fact, C phase. We see the behavioral sources here, and here's the expression, and then it goes to the gate. I've put here 50 ohm. Perhaps it's a little bit too high, so probably a 10 ohm will be more appropriate for the frequency we're working at, which is 60 hertz, but 50 ohm, it's, I guess, okay for such a low frequency. And here is the expression. It says, let me start with here, this one. If phase C is larger than A and larger than B, then you turn on this one. And you turn this one if C is smaller than B and smaller than A, as we have seen before. So this will turn on its time, and this will be turning on its time. This is the output, and this is actually the load, which is 1 ohm. So this is very, very simple. You just write the expression, and that's it. You don't have to put in logic gates and decisions and or, and, etc. And here is a output. We see here the voltages of the transistors. These are the voltages of the transistor. This is the total output. Here's the ripple. And these are the voltages. And these are the gate drivers, drive for these same transistors. So we see that when the gate drive is high, the transistor is conducting. Perhaps at the very beginning, a little bit the diode is conducting, but then the transistor is turned on. And these are the all the 6 transistors. And also here, we can see the current, very, very nice. This is the 3 phases. And these are the currents of the upper transistors, I guess, showing the current through conduction. Okay, so these are the FETs, and this is the line current. So this brings me to the end of this very short presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.